Hi, how's it going? My name is Carl Diaz. I'm with the Learning Resources Center at the University of Colorado, Denver. And today we're going to be talking about free body diagrams. This will be a two-part video where we're going to do the free body diagrams first, then we're going to do the equations associated with these free body diagrams, or how you get the equations from the free body diagrams. In the second video, so be sure to watch these together, make sure everything's correlating for you so that you understand what's going on. All right, before we get started, I think it's good to just refresh on what a free body diagram is. A free body diagram is going to be showing the object of interest, so whatever the question's asking you about. If they're asking you about a person pushing a box, then we don't need to be drawing free body diagrams on the person. If they're asking how fast the box is going to be going after it's pushed for a certain amount of time, they're asking about the box. That means the box gets the free body diagram. The person's pushing it. We can put the force from the person pushing on the box, but we don't need to draw the person there, and we don't need to draw a free body diagram on the person. It's irrelevant unless they're asking us about the person. Okay, so free body diagrams are the forces being applied to an object, and then you can put off to the side any indication of motion or change in motion, right? Velocity is your motion, acceleration is your change in motion, so for speeding up, slowing down. Velocity is just showing your direction of which way you're moving. You have your coordinate system, which is very, very important because that's how you get the signs for your equations in terms of what's going on the free body diagram. So yeah, that's pretty much what a free body diagram is. Make sure that you understand that because that's why we're doing this. Also, I see a lot of students fight this. A lot of students, for some reason, don't want to do a free body diagram because they feel like it's what babies do, or I don't know, they feel above it. I feel like people who don't understand what's going on, they're going to be the ones that draw a free body diagram. Just to teach me, the professor draws a free body diagram. All of that is absolutely untrue. Every physicist with a PhD that I've ever met draws free body diagrams, okay? So it's important the reason why I say that is important to understand that if they're drawing free body diagrams, right, someone who really understands physics, then you as a student need to be doing it. If you're trying to get out of it or weasel out of it, you can say, oh, well, I don't need that, or telling you that's not how physics works, and that's not how you're successful in the class. You should be doing what other people are doing who are successful in physics, right? And free body diagrams are the essence of being successful in physics. If you can't do this, you won't be able to do physics. And if you can do this, the physics becomes a lot easier. All right? So again, just to get started here, we got a very simple situation with a box that's just sliding. Has constant velocity, there's no friction, there's nothing pushing it. It would say that, right? The box is just sliding. And keep in mind, if the box is sliding, that means there's no force in its x direction, in this linear direction, if there's no friction as well, right? So if there's nothing pushing it and no friction, there's no force applied to the box in that x direction, right? Even though it's moving, and you can think of that as like a soccer ball when you kick it, right? The minute it leaves your foot, there's no more force from your foot onto the ball, but the ball's still moving, right? So again, you want to think that way. So this box is just sliding on some ice or something like this. So there's no forces in its x direction, all right? And then in terms of its y, it's balanced, right? The box is putting weight down on that surface. That is what mg is. That is your weight. And that surface is applying a force back to him. Newton's third law, right? Every applied force is going to have a force partner, and the normal force is going to be your force partner to your weight, right? It might not be the full normal force. Sometimes it might just be a piece of your weight is equal to the normal force, or vice versa. But you want to know that the normal force is going to be your force partner to your weight. It's going to be the force that's applied back from any applied force onto a surface. So if I press on this wall, I'm applying my weight towards the wall. But the wall is pushing back on me because otherwise I'd be falling through it. And so since I'm in equilibrium here, there must be a force pushing back on me, and that's the force we call the normal force, all right? So just keep that in mind. There's also one when I stand here on the ground, I'm putting all my weight down. The floor is pushing back on me, and that force that the floor is pushing back on me from is the normal force. If you're not on a surface, like a surface that's flat on the ground, like on the surface of Earth, you might be hanging from a string or have tension. So tension can replace the normal force, and it'll work just the same. If you're balanced, that tension is going to match the downward weight. right? If you're falling or being pulled up, that it's going to change. Tension will be more. These types of things or less in those situations. So that's what the normal force is. Keep that in mind, all right? Because the normal force is everywhere. You're going to see it a ton. And that's what's here in this free body diagram. So in these, if you notice, these vectors are the same size. That's what they should be. Okay, that's showing that they're the same value. Again, vectors are physical representations of actual numbers. So their lengths are indicative of that. And since this is balanced, it's not moving up or down, speeding up or anything like that, these should be the same length. And that's exactly what we see in that picture. All right, so for our next situation, we have a box that's now on a surface that has friction, and it's being pushed this way, and it's speeding up. Okay, so, someone's pushing on it, and as they push on it, it gets faster and faster, right? All right, so what do we need in terms of a free body diagram for that? Again, we don't need to draw the person pushing this. No one cares about that. You don't need to do it. If you're an artist, that's great, but we don't need that. That's the nice thing about a free body diagram is you don't need to be an artist. We're just trying to look at the situation. But there is someone pushing the box, and you want to draw that force on the box. Okay, so there's a force pushing the box this way, and we know because it's moving, speeding up in this direction, right? It has friction, and we know friction opposes our motion, right? So if I'm moving this way, friction is going to be this way, right? If I'm moving this way, friction is going to be this way. In this case, I'm pushing the box this way, so friction is going to be in the opposite direction, which is what that force is. And since we're speeding up, that means there's a net force in a certain direction. So this should be longer than this. It has to be, right? That's a correct way to look at it. Now over here, I kind of emphasized some things and drew things bigger than they should be, but these are correct. You have to keep that in mind. I'm going to stress that here because that is what you want to be. That's what you want to have when you're giving your answers or doing these free body diagrams, okay? If they're balanced, they should be the same size. If they're unbalanced, they should be different sizes. Okay, and then the box is sitting on a surface, right, as it moves across the floor here. So there's going to be some weight applied to that floor, and the floor is going to be pushing back on that box, keeping it balanced and not letting it fall through the floor, and that's the normal force. Now, we are moving in this direction, so we're indicating that, and we are speeding up in this direction, and so we are indicating that, and that's what the acceleration and velocity are showing. And that's it. There's nothing more to that free body diagram. That's pretty straightforward. All right, so now let's look at some boxes moving on at an angle. Okay, this shouldn't get any more complicated, but just like we saw from our vector video, when we start to have components that or vectors that don't sit exactly along the x-plane or the y-plane, we have to break those vectors up into components. And so when we start to move at a banked angle here, this box is sliding down, this box is sliding down here, the Cartesian coordinates fall along the plane. So now you can see instead of x, y being here, right, or x direction here, y being here, we have x here and the y is now here, right? Here's my y's showing that direction, and these are my x's. Okay, so that lets us know that there's an angle here, that one of those vectors are going to be sitting at an angle, and in this case it's the weight, and you want to break that up into its components or its pieces. All right, if you're confused about that, go watch the vector videos because we talk about what components are, their pieces, how they work, why you want to get them, right? That these pieces make the whole. All right, and we can also see what pieces are being balanced here. We'll talk about that here in a second. All right, the other thing that we know, and it's because of geometry, you don't have to know why, but this angle and this angle are going to be identical. All right, so when you draw MG, all right, and then you make the components of MG, you can go ahead and put the angle that's here on the ramp, the same angle from the ramp, in between, right? It could be the angle between your vectors here that's forming the right triangle, right? So this should form a right triangle with that being the angle for that right triangle. That's matching that angle of the ramp. Alrighty, so that's what we're doing here, all right? So for the problem tells us there's no friction, right? It's sliding down the ramp and it's speeding up. So we have some rate of motion, change of motion, speeding up down the ramp. Have that. The velocity, we know it's moving down the ramp. That's what that's indicating, right? Now we want to look at the forces. Again, this box is pushing against the ramp, so there's going to be a normal force, right? Which is going to be opposing the weight in a sense. But here's a great example of where the normal force is not equal to the entire weight, or mg. Since mg has components, part of mg is going to be balancing out the normal force, right? That's going to be the weight actually being pressed down on the ramp. And the other piece of mg is going to be the component that's actually pulling the box down the ramp. All right, so this force, which is part of the weight, is actually the force pulling the box down the ramp, and it doesn't exist down here in the ramp. We draw it down there so we can get the picture, so we can see where it's at, but you want to make sure that you're moving that vector up here, because that vector is actually right there. That force is being applied to the box and pulling it down. All right, so again, we have these two pieces. The two pieces are the green pieces compared to this blue vector, which is the whole weight. And again, if you were to add these two pieces, these two components together, you would get the weight. All right, and you want to label those up. So this component, right, because of the angle, right, it's associated with, it's adjacent to that angle, so it's going to take on the cosine. Again, this mg is the hypotenuse of this right triangle, and then cosine is going to be the trigonometric function associated with that. And then this is in the negative y direction, so you want to make sure to get that a negative sign, okay? Now again, we're labeling this on this picture because we want to see those forces. Just like we have mg, these forces have a label themselves, and this is mg cosine theta. This is not mg. We want to label it as such. This vector right here is mg sine theta, and it's in the positive, pointing in the positive direction, so it gets a positive sign. That's how it gets that, all right? And we'll talk about that more when we go and do the math. When we write the equations down, that will be more important. Okay, and that's what's going on. And that's pretty much all that's going on in this picture. It's being balanced. There's no friction opposing the motion of the box. So the friction would go up the ramp if there were some, but there isn't. So it's just moving down the ramp. As it moves down the ramp, it's speeding up. The reason the force pulling it down the ramp is a component of the weight, right? And the other component of the weight is balancing out the normal force. And we'll definitely see that when we write our equations. It'll be crystal clear in the equations. All right, that who belongs to what? All right, what value belongs to what? All righty. So now we have an even more complicated situation, right, where this box is being pushed up the ramp with friction, and it's slowing down. So they're pushing it up, and as they push the box up the ramp, the box is getting slower and slower and slower. So again, we don't need to draw the person pushing the box. That is irrelevant, but we do want to put the force that person's pushing the box on. So we have that, and that's up the ramp, as we know. Okay, and our Cartesian coordinate system, again, matches the angle of the ramp. So the x is going to be along the plane of the ramp, and the y is going to match the normal force direction. All right, and so we have the push of the person, right? And then we have the weight. We saw here that there's always going to be a weight component going down the ramp from a box that's sitting on a ramp or moving on a ramp. It'll always be there because the weight will always be distributed into components, all right? And so there's always going to be a piece of that weight that's going to be pulling it down the ramp. Even when you're moving up, you're counteracting that force, okay? Or if you were to let it go, that would be the force to pull it back down the ramp. When you would let it go, something has to be pushing it, otherwise it would stay still. All right? So, we have the force from the push, we have our friction, because we have friction that's opposing our motion, right? And then we have the component, right? We have our weight, and our weight is then broken up into components for the same reason that we did up there, where this y component becomes negative mg cosine theta because of the negative y. Now this, if you noticed, we've switched Cartesian coordinates. Here this was positive x, here this was a negative x. You got it, you can do that, but you've got to make sure that you're taking account of it. And so we see right here that this negative sign is associated with mg instead of the positive one that we have up here because of the direction that it's going. Okay, now remember, we've always said Vectors, a sign with a vector is because of its direction, not because it's less than 0. So don't forget that, and that's on several videos we see that. So again, we have our weight, our normal force, right? There's two components of our weight. Part of the weight is balancing out the normal force, or balancing this box on this ramp. The other part of the weight is pulling the box, or it's pulling the box down the ramp. And even though we're moving up, it's pulling a force down the ramp on the box, or applying a force down the ramp on the box. There's also friction there. Remember, friction's only in play if we're moving. There's static and kinetic friction. And so, but that only comes when you start to apply the force to the object. So that's also there because of this. So we have these two things opposing that. These should add up to be larger than this because it's slowing down. There's some net force now down the ramp, which we can indicate it with our acceleration. See here, we were speeding up and the acceleration was in the same direction as our box. Here we're slowing down. We're pushing the box up the ramp, but we're slowing down. So our change in motion, acceleration is going to be in the opposite direction. Okay, and that's why we're slowing down, because this friction and mg are larger. There's a net force down the ramp versus our force of pushing the box up the ramp. Alrighty, so that's it for that one, pretty straightforward. Now we have two looking at tension. Let's go ahead and start with this one here. So this is a box being pulled at an angle, right? So you're, think of it like a sled on the ground and you're pulling at it like this. So the rope is going to sit at an angle when it's attached to the sled when you're pulling on it. So you're pulling the box or the sled or whatever it is at an angle with a rope, and that's what that's trying to indicate, and that's tension. We've got T there showing the tension there. All right. We're moving at there is friction here, but we're moving at a constant velocity. All right. So again, when we have vectors that are at an angle, you need to break them up into components. You have no choice. You have to do it, okay? Because we have to look at how those components are working in their x and y directions independently, all right? Remember, these components work independent of the main vector. This t sine theta, for example, is working in the y direction, and this t cosine theta is working in the x. There's none of the t sine theta in the x direction. There's none of the t cosine theta in the y direction, okay? So they're independent of themselves, but when they're added together, we get the whole. So we have to break up into components, all right? And the other reason why that we explained in the vector video is because we have to add these components together, and you can only add x's with x's, y's with y's, right? So that's the thing. That's why you always want to break into components. So we're being pulled at an angle, so that's the tension that we want to break up into its components. So we know the angle off the surface, which is that, and we know the tension will break up into its x component and its y component, which are both vectors, and we don't want to label those as such, right? So this, because of its association with that angle, right, it's adjacent to that angle, it gets cosine, and this vector is opposite of that angle, so it gets the sine, right? They're both in the positive, right? Positive y is up, positive x is this way, so they're both pointing in the positive direction, so they both get positive signs, all right? Here we got the normal force balancing out the mg. Now it's sitting on a flat surface, right? Everything is flat here, and so we know everything is balanced, and there should be equal sizes, and this mg should have a negative sign. We'll put that there for when we start the next video, but just keep that in mind, staying consistent with everything. I should have been putting, well, I took care of it there, but I probably should have put a negative there, a negative with that mg, and a negative with this one. We will have those on the next video, but those should go there. And then we have the opposing friction, which is this way, right? It's opposing the pull, right? We're opposing it, but it should be balanced, right? So we see that this t cosine theta and this friction are the same size, and they should be because they're balanced. It's moving at a constant velocity, which means the forces in the x direction, whether positive or negative, they should be balancing themselves out. Newton's first law, right? So we know this. Newton's first law is about balance, and we know that the t cosine theta is balancing out the friction here. And we also know that this normal force and t sine theta, they're working together to balance out mg, okay? So these two added together balance out the weight, all right, or the y component. And so that's everything we have for that free body diagram, pretty straightforward. And this last one's very easy. You could also have free body diagrams that are very similar to this that are in free fall if you have drag. So you could think of it the same way. But this is just a box hanging on a rope, right? If it was swinging or if it was at it being held at an angle over here, you would use this same technique. The tension would now, if the rope's sitting at an angle, the tension would be at an angle. You'd want to break that into components, apply those components to the box, how they're applied to the box, and then go forward from there. But here we just have a box just hanging straight down. So there's tension pulling up on the box, and there's weight, right? The weight of the box pulling down. Those are equal and opposite. The box is sitting there. If they weren't equal and opposite, the box would be falling or break the rope, or the tension was more than the mg, the box would be moving up because the tension would be pulling up on it. There'd be some net force. There's just a balance of forces here. It's just hanging there. It's in equilibrium, and that's Newton's first law. Again, the same thing happens in free fall. When a ball's falling through the air, if there's drag, eventually the drag is going to match the weight, and it's going to get to a constant velocity. Or if there's no air resistance, then there's just going to be some net force downward, and it's just going to speed up, speed up, speed up, and never stop. All right? So this is the free body diagram video. Hope it was helpful. Please watch the second video that's going to be associated with this. That is going to be showing us the equations and how we get the equations from the free body diagram. Thank you so much for watching. Keep in mind to go to class. These are supplementary, so when you're watching these with class, things should go together. I'm super proud of you. Keep up the good work.